Hi, I'm Miss Hearn. Let's get started. We're going to talk about the direct comparison test for convergence or divergence of improper integrals. If you find the video helpful, please remember to give it a thumbs up. That helps other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos. As you can imagine, there are many cases where the improper integrals, we just can't evaluate them. Okay, the integrand is just too difficult. However, what we can do is use certain techniques to at least determine if it converges or diverges. I want to show you two different tests that we can use to determine if an improper integral is going to converge or diverge. And both of them are called comparison tests. The idea is actually what you brought up earlier when you said, oh, if the integral from 1 to infinity of 1 over x squared converges, then it must mean that the integral from 1 to infinity of 1 over x cubed converges. Is exactly what the type of thing that we're doing. So we're saying, oh, well, if this integral converges and this integral is smaller than that one, it has to converge too. Or if I know that this integral over here diverges, and this one's even bigger than that, it has to diverge too. And that's called the direct comparison test. It says, let f and g be continuous on the interval from a to infinity, where f is smaller than g. That's what this means here. F is smaller than g for all x greater than or equal to a. Then, if we know that the larger function converges, then it must mean that the smaller one does. Remember, converges means it's a finite area. So if you have a larger integral with a finite area, then the smaller one must also have a finite area. On the other hand, if the smaller function diverges, if it's infinite, then certainly a larger one must be infinite as well. So we can compare known integrals to unknown ones and at least figure out if the integral converges or diverges. If we want to establish that an improper integral that we don't know is divergent, would we want to compare it to a larger divergent integral or a smaller divergent integral? That's right. If a smaller one diverges, then certainly the larger one does. If we think that an improper integral is going to converge and we're trying to establish that, we would then want to compare it to a larger convergent integral, because certainly if the larger one is not infinite, then the smaller one isn't either. So that's the direct comparison test. Nice thing about these comparison tests is you're not actually integrating. So let's say that we want to compare the integral from 1 to infinity of 1 over x squared plus 1 dx to the integral from 1 to infinity of 1 over x squared dx to show that the first one is convergent. Why would I compare those two in particular? If this is my unknown, why would we choose this guy to compare it to? What about it is easier? Let's start with that. The larger and smaller is also important. Yes, this is one of those special ones that we have a formula for, so we don't ever actually have to integrate. So first of all, we use those a lot in comparison tests because we know them. And so this is definitely known. And we can, in fact, we know it converges to 1 over p minus 1, which is 1 over 2 minus 1, which is 1. Okay, so that's significant. Okay, we want to establish the unknown one is convergent. Do we want the known one to be larger or smaller? If we think an improper integral is convergent, we compare it to a larger convergent integral. Because if the larger one's convergent, so must the smaller one be. We want the unknown one to be smaller than a known convergent one. Then it has to also be convergent. We're going to, number one, state the claim that the integral from 1 to infinity of 1 over x squared plus 1 dx converges. Okay, in order to prove it, we prove that a known convergent integral is larger than that one. The known integral that we're going to work with is this one. That's known. We want to compare 1 over x squared to 1 over x squared plus 1. It usually comes down to looking at the denominator. Not all of them, but so which one has a bigger denominator? Bigger denominator means a smaller number, right? It's like, for example, 1/2 is bigger than 1/3. Bigger denominator, but with the same numerator, is actually going to be the smaller number. You can say that 1 over x squared is bigger than 1 over x squared plus 1 because x squared plus 1 is bigger than x squared. The one with the bigger denominator is the smaller fraction. You with me on that one? Okay. You have to establish that. You prove that the known integral is convergent. How do we prove that the known integral is convergent? Well, we know the integral from 1 to infinity of 1 over x squared dx p equals 2 is greater than 1, which means that it converges to 1 over p minus 1, which is 1 over 2 minus 1, which is 1. You got to write that out so that the person who's reading it knows your reasoning. So I really should put comparing to this, which is a larger. All right, and then since the integral from 1 to infinity 1 over x squared dx converges and 1 over x squared is greater than 1 over x squared plus 1, we conclude that the integral from 1 to infinity of 1 over x squared plus 1 dx converges also by the direct comparison test, which I frequently abbreviate as DCT. So we just showed convergence, but remember on the direct comparison test, you can also show divergence. So let's look at one where we're going to show one is divergence. So this one says, use the direct comparison test to show that the integral from 1 to infinity of 1 over the square root of x squared minus 0.5 dx diverges. Our claim is that the integral from 1 to infinity of 1 over the square root of x squared minus 0.5 dx diverges. To establish that claim, we need to compare it to a known divergent integral that is smaller than that one. Now, smaller means it has a smaller or bigger denominator, a bigger denominator. So we're thinking bigger denominator. Very good. So right now, 0.5 is being subtracted from x squared. So wouldn't it be true that 1 over the square root of x squared minus 0.5 would be actually bigger than 1 over the square root of x squared? Would that be true? Yes, because I just made the denominator bigger, so I made the fraction smaller, right? But what's that equal to? 1 over x. Do we have any information about the integral from 1 to infinity of 1 over x? P equals 1, so it diverges. That's right. So prove that the known integral is divergent. The known integral that we're going to use is the integral from 1 to infinity of 1 over x dx, which has a power of 1, which is less than or equal to 1, so it diverges. Okay, so what does that mean? We have just shown that a smaller integral, the smaller known integral from 1 to infinity, 1 over x dx diverges. So by the direct comparison test, the integral from 1 to infinity, 1 over the square root of x squared minus 0.5 dx also diverges. So to work these problems, we will frequently use integrals of this form as our known integrals. And we have to keep in mind that when two functions have the same numerator, the one with the smaller denominator is the larger function, and the one with the larger denominator is the smaller function. Hi, I'm Ms. Hearn. If you like this video, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Ms. Hearn Mathematics, for more math videos.